Did you know that each time you integrate, that essentially you're solving a differential equation? That's what we're going to focus on in section 1.2, integrals as general and particular solutions. Throughout chapter 1, we're going to look at several different methods for solving differential equations, and the most fundamental and basic way is by direct integration. Let's consider first-order equations. If dy over dx equals f of x and y takes the form dy over dx equals f of x, that is, if we have a first-order differential equation where we can isolate the first derivative and get it equal to a function of x alone, then we can solve by direct integration. If on the other side of that equals there happens to be the dependent variable, then we will not be able to use this method. We'll look at other methods for that situation. So if we can isolate the first derivative and it's equal to a function of the independent variable alone, then the solution y of x is equal to the integral of f of x dx plus c, or if you want to use antiderivative notation, big F of x plus c. This is called a general solution to the differential equation obtained by direct integration. General because c is an arbitrary constant. Given an initial condition, y of x naught equals y naught, a particular solution can be found by noting that c equals y naught minus big F of x naught. So to solve a differential equation by direct integration, first of all, the derivative has to be isolated and equal to a function of the independent variable alone. We will integrate both sides with respect to x. Because of the plus c with all indefinite integrals, we obtain a general solution. And then we plug in the initial condition to determine c, and that leads us to a particular solution. Now, just a quick reminder, whenever your variables have subscripts, they represent values. So those are going to be real number values there that we're plugging into our solution. This is a very simple and straightforward process, so let's try example 1. Solve dy over dx equals cosine of 2x, subject to y of 0 equals 1. Remember, this is what we call an IVP, or initial value problem. Because the highest derivative that we can find in this differential equation is the first derivative, we're dealing with a first-order differential equation. So let's solve by integrating both sides with respect to x. Notice the Leibniz notation. We're going to integrate the first derivative with respect to x. So I've got the extra dx there. And applying the same operation to the other side, we're going to integrate with respect to x. Remembering that the differentials in the Leibniz notation behave algebraically, we can cancel the dx's. And on the left side, we're left with the integral of dy, which just becomes y. On the right side, the antiderivative of cosine of 2x is 1/2 sine of 2x plus c. Note that on the left side we have our dependent variable y. It helps also to understand that y is a function of the independent variable x. So I'm going to go ahead and include the argument in my solution here. This is the general solution to the differential equation. General again because we have the arbitrary constant c. To find the particular solution, at this point, we need to apply our initial condition. The given initial condition was y of 0 equals 1. What's in parentheses is the independent variable's value. So we're going to plug 0 in for x, and we're going to plug in 1 for y of x. So we'll solve 1 equals 1/2 times sine of 2 times 0 plus c. Our goal is to solve for c. Now, sine of 0 is equal to 0, so we can quickly see that the value of our arbitrary constant here is 1. If we take this information back up to our general solution and plug in 1 for c, that will give us our particular solution. So in this case, the particular solution is y of x equals 1/2 times sine of 2x plus 1. Now it's important to recognize here that the actual differential equation has an infinite number of solutions. Those are represented by that general solution with that arbitrary constant c. We can view that as representative of a family of solutions. So I'm going to graph several particular solutions over here, including the one that we found, so we can have a good concept of the overall solution to this differential equation. Considering y equals 1/2 sine of 2x plus c, we're going to have sinusoids or sine waves with a period of pi. Also, the amplitude there would be 1/2. So assuming that c is equal to 0, we're going to have an ordinary sine wave with an amplitude of 1/2. That's what it would look like for c equal to 0. If we allow c to be 1, this just translates our entire function up 1 unit. If we're thinking about transformations, so we end up with a sine wave looking something like that. That would be our particular solution. For c equal to 2, we'd have a sine wave up here. C equal to 3, something like this. So again, that general solution is forming a family of curves. Each one represents a particular solution. And the way we distinguish between particular solutions is based on an initial condition. So congratulations, we have just solved our first differential equation for the semester. It was a first-order differential equation. We solved it by direct integration. Then we applied an initial condition to move from general solution to particular solution. So pretty straightforward and simple. Let's try example 2. Solve dy over dx equals x times the square root of x squared plus 9, subject to y of -4 equals 0. Notice that our first derivative is isolated, and it's equal to a function of the independent variable x alone. Therefore, we know that we can solve it by direct integration. So once again, we're going to integrate both sides with respect to x. We will see the same pattern with the differential terms on the left, where we end up with the integral of dy, which is just y, or we can be specific and write it in function notation y of x. Now, on the right side, we do have to determine an appropriate technique of integration. In this case, a U-substitution will work. If we choose u to be the integrand, x squared plus 9, then du will be 2x dx. Notice what's left over in the integral other than what we chose for u is x dx. We can replace those leftovers with 1/2 du. So our new integral in terms of u becomes the integral of the square root of u, or I'm going to write it as u to the 1/2, times 1/2 du. So for y of x, we'll end up with, I'm going to move the 1/2 out in front of the integral. We're going to integrate u to the 1/2 to get u to the 3/2 divided by 3/2, or times 2/3. And then don't forget the arbitrary constant. Let's simplify and rewrite in terms of x. So our general solution is y of x equals 1/3. I'm going to replace u with its original expression in terms of x, x squared plus 9, to the 3/2 plus c. So this is the general solution to the original differential equation. It yields a family of curves. We want the specific curve that satisfies the given initial condition. So the initial condition is y of -4 equals 0. So we're going to plug -4 in for x, 0 in for 1. We obtain 0 equals 1/3 times -4 squared plus 9 raised to the 3/2 plus c. Let's figure out what's inside parentheses. 4 squared is 16. 16 plus 9 is 25. So we need to evaluate 25 to the 3/2 power. To make that easy to understand, I'm going to rewrite it in radical notation. 25 to the 3/2 power is the same thing as the square root of 25 cubed. The square root of 25, of course, is 5, and 5 cubed is 125. So it looks like our c value then is -125 over 3. So we can plug that in for c in our general solution, and we can upgrade from general solution to particular solution. We obtain y of x equals 1/3 times x squared plus 9 to the 3/2 minus 125 over 3. So we have solved the differential equation by direct integration and applied the initial condition to get a particular solution. Later in this section, we'll begin to get an understanding of what the initial condition actually represents as we examine some models. Let's try one more solution by direct integration. We have the first order differential equation, dy over dx equals 4 divided by x squared plus 9, subject to y of 3 equals 0. Because our first derivative is isolated and it's equal to a function of the independent variable alone, that's the green light for solving by direct integration. Later in this chapter, we'll learn what to do if this right side is a function of both x and y. Our approach will be a little bit different in that case. On the left side, you're seeing this rhythm. We're going to get y. And over here, we have 4 times the integral of 1 over x squared plus 9. Now, you could evaluate this with trigonometric substitution, but I do hope that you recognize this is a simple pattern. If you haven't yet memorized the formulas associated with integrals that yield your inverse trig functions, now would be a good time to do it because we're going to use these quite a bit. This yields 1/3 arctangent of x over 3 plus c. We'll evaluate those integrals quite often, so taking the time to evaluate such a straightforward basic one using trig substitution will really be taxing on your mind and your patience. So hopefully you can recognize that formula. And if you don't recognize the formula, let me be very clear here. We're looking at the integral of 1 over x squared plus a squared, and I can be even more general here. A function of x squared, we'll call it u squared, plus a squared, du. The antiderivative is 1 over a, arctangent, u over a plus c. So add that to your memory bank if you have not done so already. And by the way, you can write it as arctangent or inverse tangent. Either of those would be acceptable. So our general solution then is y equals 4/3 arctangent of x over 3 plus c. Now, as you're going through your work, it is very helpful to label the specific milestone. When you reach that general solution, go ahead and label that the general solution. It helps me to follow along with your work, and it also helps you to go back and easily refer to that general solution. Now we're ready to go to a particular solution. And remember, to do that, we apply our initial condition. So we'll plug 0 into our function for y, and we're going to replace x with 3. So we're going to evaluate arctangent of 3 over 3, and we're going to use this to solve for c. So we're evaluating arctangent of 1 or inverse tangent of 1. That's going to give us pi over 4. Be absolutely certain that you know how to evaluate that exactly. Never round unless asked to do so. Use exact calculations as a rule of thumb in this class. So it looks like c is negative pi over 3. We can use that to update the arbitrary constant in our general solution, and then we can express our particular solution. We would obtain y or y of x, function notation or not, either way is fine, equals 4/3 arctangent or inverse tangent of x over 3 minus pi over 3. And that's the particular solution obtained by solving with the method of direct integration. The method of direct integration can apply to first order or second order equations. Let's look at how it's a little bit different with a second order differential equation. Given the second derivative of y with respect to x equals g of x, again, please notice, in order for this method to work, this must be a function of the independent variable alone. Otherwise, direct integration will not get the job done. So we have our second derivative isolated. It's equal to a function of the independent variable alone, which in this case is x. So g of x does not involve the dependent variable y or its first derivative. So in this case, we're simply going to integrate both sides with respect to x twice. So let's practice this process and find the general solution to this differential equation below. So our differential equation is the second derivative of y with respect to x equals a function of the independent variable, or g of x, alone. We're going to solve by integrating both sides with respect to x. So on the left side, we'll have the integral of the second derivative of y with respect to x, and we're integrating with respect to x, equals the integral of g of x also with respect to x. So we are applying the same process to both sides. That is, we're integrating with respect to x. Now, again, Leibniz notation behaves algebraically. So I'm going to cancel one of those dx's on the left, and we are going to end up with dy over dx. So we're integrating with respect to x. One way to think about it is we're integrating the second derivative, and that yields the first derivative. Now over here on the right side, since we're doing this in general, I'm going to express the antiderivative of little g as capital G of x. That just shows that we will have executed the integration process at that time. And I'm going to go ahead and subscript my constant, because as you're going to see here in a minute, we're going to obtain two arbitrary constants with a second order differential equation. So we have gone from a second order differential equation now to a first order differential equation, and I'm going to solve this again with direct integration. So we'll have the integral of the first derivative, dy over dx, with respect to x, equals the integral of g of x plus c1 with respect to x. So on the left side, we have the integral of dy, which gives us y, or you can write it in function notation, y of x. Over here on the right side, since we don't have a great way to represent this in general, I'm just going to apply that integral operation to the first term. Then when we integrate the constant c1 with respect to x, we get c sub 1 times x, and then we're going to need one more arbitrary constant to go with that second integral there. So this would be our general solution. Notice we have a two-parameter family of solutions. So in order to solve for those arbitrary constants, we would need two initial conditions. So with a first order differential equation, we need one initial condition to get a particular solution. With a second order differential equation, we're going to need two conditions to get a particular solution. But notice in each step, we were simply integrating both sides directly with respect to x. Now, if you understand everything that we've done so far, then that is really the heart of this section. Solving differential equations by direct integration, that includes first order and second order. The challenging part of this section is the application. We're going to review velocity and acceleration models and do several examples. These differential equations will all be solved by direct integration. So recall that if a position function is defined x of t, where it's a function of t for time, then the velocity function is the first derivative of position, and the acceleration function a of t is the second derivative of the position function. This can be denoted with Leibniz notation or dot notation. For dot notation, we would say the velocity function is the first derivative of x, and the acceleration function is second derivative of x, which we could denote x double dot. We could also recognize acceleration is the first derivative of velocity. So if we take those relationships, position, velocity, and acceleration, and combine it with Newton's second law, which states that force is equal to mass times acceleration, or in terms of a function, force as a function of time is equal to mass times acceleration as a function of time. If we put all of this together, we can come up with a comprehensive model for motion. These motion equations will govern both vertical and horizontal motion. So let's begin by deriving a vertical model. The weight W of a body is the force exerted on the body by gravity. So recall, weight is a force. Thus, force equals mass times acceleration becomes weight equals mass times gravity. So essentially it's the same law. We're just looking at it from the perspective of weight. Using the relationship between position, velocity, and acceleration combined with Newton's second law, we can generate a system of equations that govern motion. Suppose that g represents constant acceleration of gravity on Earth. Determine the velocity and position functions, v of t and x of t respectively, of an object in motion at time t. And let's correct my typo here. For the vertical model, we're going to use y of t for position. Later, we'll use x of t in a horizontal model. So we are going to look at initial position y naught equals y of 0 and initial velocity v naught, which equals v of 0. So beginning with our acceleration function, if our acceleration is represented by the constant g, then velocity is going to be the integral of acceleration, or the integral of g with respect to t. So our velocity function then is gt plus constant, we'll call it c sub 1. So we solved here the first round of direct integration. We went from second derivative, now we've arrived at first derivative. Let's go ahead and apply our initial condition. Initial velocity is equal to v of 0. So our initial condition is v of 0 equals v naught. So we're going to replace the y constant, or v of t, with v naught, and we're going to plug 0 in for t, and we'll solve for c1. G times 0 is 0, so the constant that we're interested in here is v naught. So our velocity equation then is g times t plus v naught. So if our acceleration function is g, then we can expect that our velocity function will be gt plus initial velocity. If we go through one more round of integration, that is, if we integrate velocity, we will obtain position, and we're going to integrate the right side of this equation with respect to t. We'll end up with gt squared over 2 plus v naught t plus a second constant of integration. Let's go ahead and apply our second initial condition to make this a particular solution. At time 0, position is y naught, so we can plug y naught in for y on the left side. We can plug 0 in for t, and this will allow us to solve for our second arbitrary constant. So the second arbitrary constant here we're simply recognizing is initial position. So our position function then is, you can write it gt squared over 2, or here's another option, 1/2 gt squared, either way is fine, plus v naught t plus y naught. So all we did there was integrate twice with respect to t to progress from acceleration to velocity to position. Now the three boxed equations here represent a system of equations that govern motion or describe motion. So when we're working a specific example that has acceleration, velocity, and position, we don't have to continue solving these differential equations over and over again. We can expect the model to fit these equations. For example, let's apply it to this situation. Example 4, a baseball is thrown straight downward with an initial speed of 40 feet per second from the top of the Washington Monument, standing 555 feet high. How long does it take to reach the ground, and with what speed does the baseball strike the ground? Before we tackle this problem, let's glean the important information. First of all, we are told that the initial speed of this baseball is 40 feet per second, and we're throwing it straight down. In a vertical model, up is positive and down is negative. So we can say the initial velocity, v naught, then is negative 40 feet per second. In addition, we know that the Washington Monument stands 555 feet high. That's initial position, 555 feet above the ground. Observe in this case that the unit, the linear unit for distance here, is feet. So the value that we will use for gravity is negative 32 feet per second squared. The particular textbook that we're using uses negative 9.8 meters per second squared if our distance is measured in meters, and negative 32 feet per second squared if our distance is measured in feet. Now, the system that we're going to use for this, without need to solve an additional set of differential equations, we can say the position y of t above the ground is negative 16t squared. Remember, we had 1/2 gt squared. That's where negative 16t squared comes from. Minus 40t plus initial height 555. So again, where that's coming from, I'm using this model that we've already derived. We're plugging in negative 32 feet per second squared for g. We're plugging in negative 40 for initial velocity and 555 for initial position. So again, once we have developed that model in general, we can simply attach our specific values to model this situation. Next, we need our velocity. Now, you can either remember what velocity looks like or you can just differentiate, right? The first derivative of position is velocity. And then one more round of differentiation, we end up with acceleration equals negative 32. So we have our parameters, we have our system. Remember, we're on the top of the Washington Monument throwing a baseball straight down to the ground. Now we're ready to begin answering the question, how long does it take to reach the ground? And with what speed does the baseball strike the ground? How long does it take to reach the ground? Well, let's come up with a game plan. The first thing that we need to do is figure out how long it takes to reach the ground. So we need to find t when the height or position is 0. Again, this is when the baseball strikes the ground. So we know that we'll be using this equation. If we set the height of the ball equal to 0, and we solve for t, then we will have answered that first question. Now, taking a look at this quadratic equation, probably not going to be able to factor this one, so we will apply the quadratic formula. So t is equal to negative b, that's going to be positive 40, plus or minus the square root of b, that's negative 40 squared, minus 4 times a, which is negative 16, times c, which is 555, all divided by 2 times a, or 2 times negative 16. If we plug that radicand into our calculator, we're going to end up with the square root of 37,120, and we have a negative 32 in the denominator. Now, if we took the time to find the prime factorization of this radicand, 37,120, we discover it's 2 to the 8th times 5 times 29. We can use that to simplify this radical exactly. We would obtain 40 plus or minus 16 times the square root of 145 over negative 32. So that gives us our two exact solutions. We want to keep our calculations exact as long as possible in order to avoid rounding error. So now we can go ahead and approximate. Now I'm just going to recommend you type these into your graphing calculator. I'm going to round to the nearest hundredth. The problem didn't tell me where to round, so I'm just doing this arbitrarily. We get negative 7.27 and 4.77. Now, the negative time does not make sense for our particular application, so we'll keep the positive one. And remember, we are measuring seconds. So about 4.77 seconds after we throw the baseball off the top of the Washington Monument, it's going to hit the ground 4.77 seconds later. And by the way, this one in exact value is 40 minus 16 times the square root of 145 divided by negative 32. This is our exact solution. Okay, so we're making a difference between the exact solution here and the approximate solution. Now, the second question is, with what speed does the baseball strike the ground? To figure out with what speed the baseball strikes the ground, we can use our velocity equation. So we need to find v at this particular time. Now, I'm going to encourage you to practice using your exact values in your calculations so that your rounding error is avoided. Okay, this turns out, if you plug it into your calculator, to be approximately negative 192.67 feet per second. Okay, if you use 4.77, you're going to get approximately the same thing. But keep in mind, if you are going to be an engineer, if you make series of approximations, then you do start to accrue rounding error, and that can have negative results for your particular project. So be really careful about that. So negative 192.67 feet per second. Now, how fast is that exactly? Well, I'm not quite sure. I'd rather hear it in miles per hour. So I'm going to convert it to miles per hour. We have negative 192.67 feet per second. I'm going to multiply it by 60 seconds in 1 minute. That's going to convert my seconds to minutes. 60 minutes in 1 hour. And 1 mile per 5,280 feet. Okay, I'm just using dimensional analysis here, looking at, I'm canceling the seconds to obtain minutes, I'm canceling the minutes. Now I can see I have hours in the denominator. Cancel out the feet, we have miles in the numerator. So by the way, this comes out to be, using our calculator, approximately 131.37 miles per hour. That is pretty fast. So try to see the big picture of this problem. We listed our initial values. We recognized the appropriate constant to use for gravity. We plugged those values into the system without having to solve the differential equations again. Since we did that once in general up here, now we can use those equations as they are and just update them with specific parameters. We were able to answer the questions by using that system of equations. How long does it take to reach the ground? Well, we know that when the ball hits the ground, the height is 0. So we used that in our position equation to solve for t. Got 4.77 seconds. And the next question, with what speed does the baseball strike the ground? Well, now in this case, we're using our velocity equation. We know that at 4.77 seconds, the baseball strikes the ground. So we're using that time value, plugging that into our velocity equation to actually figure out the velocity. So ultimately, we are simply manipulating a system of equations. There's not a whole lot of differential equations that we did there. Let's try another example. Suppose a woman has enough spring in her legs to jump on Earth from the ground to a height of 2.25 feet. If she jumps straight upward with the same initial velocity on the moon, okay, so this woman who jumps on the Earth to a height of 2.25 feet is going to fly to the moon, and she's going to do the same experiment. She's going to jump on the moon. So she's going to have the same initial velocity on the moon that she did on the Earth. But on the moon, the surface gravitational acceleration is approximately 5.3 feet per second squared, so much less than Earth's gravity. We want to know, how high above the surface will she rise? So this woman is jumping on the Earth. We know her parameters on the Earth. To the moon, how high could she jump if she was on the moon? So let's map out a strategy for solving a problem like this. Now, assuming this woman jumps with the same power on the Earth same power on the moon as on the Earth, her initial velocity will be the same in both locations. So this means we can say, thus, we should find her initial velocity on Earth and then use it to find the height of her jump on the moon. So we're actually going to need two sets of equations, a set for the Earth and a set for the moon. Let's begin with the model for the Earth. On Earth, the acceleration of gravity is negative 32 feet per second squared. I'm going to go ahead and recognize units here. Then her velocity would be negative 32t plus v naught. Either you can memorize those equations or just note I'm integrating here and using v naught for the arbitrary constant. The units associated with velocity there would be feet per second. Position y of t, integrating, we'd get negative 16t squared plus v naught t, and we're going to call initial position y naught. Now, if she is jumping from the ground on the Earth, which she is, then that initial position, the initial height above the Earth, will be 0. So we can eliminate that term and recognize we're measuring feet above the ground for our position. Now let's think about this woman jumping on the Earth. She's going to leave the Earth with a specific initial velocity, and she's going to reach a maximum height of 2.25 feet. So we know the maximum height. We know y of t is 2.25 feet. We don't know what time that occurs, though. But we do know that when she reaches her maximum height, her velocity will be 0 because she's at the top of her jump. So we can call this a clue for finding the information we need. We can say, when her height, y, is 2.25 feet, we know that her velocity is 0. I'm going to use that information to find t, time, the time at the top of her jump. So let's look at our velocity equation. When velocity is 0, she'll be at the top of her jump. We want to know at what time does that occur. So we can solve 0 equals negative 32t plus v naught. If I solve this for t, I'm going to move this to the other side and divide by 32. We have the time that she reaches the top of her jump, at least in terms of her initial velocity. Now, I'm going to use the position function, y of t, and I'm going to evaluate it at this particular time at the top of her jump, okay? So back to our position function. Okay, this is our position, height above the Earth, which is negative 16t squared plus v naught t. We know that y of v naught over 32, that's the time she reaches the top of her jump, because at that time her velocity would be 0. At this particular time, her height's going to be 2.25. So I'm going to plug 2.25 in for height above the ground, and I'm going to plug v naught over 32 in for t. Notice at this point we have an equation in one variable, so we should be able to solve for that initial velocity. So I'm going to move over here to have a little bit of space, 2.25. Notice we have negative 16 coefficient, v naught squared over 32 squared. So 32 squared is 1,024, and 1,024 divided by 16 gives me 64, and we still have a negative coefficient there. So again, I'm just simplifying the constants. The second term, we have v naught squared over 32. If we get a common denominator over here on the right side of 64, we'd have negative v naught squared over 64 plus 2 v naught squared over 64. That's going to give me v naught squared over 64. Multiply both sides by 64. We have v naught squared. We'd obtain 144 over here. Take the square root of both sides. We get positive and negative 12 for v naught. Now, since we're looking at the velocity to jump from the Earth, the only feasible value for our initial velocity there is the positive value. So her initial velocity then, which is important to our model, is 12 feet per second. Now that's important information because now we can rewrite the model to fit the moon. Now the acceleration on the moon, we were told, is negative 5.3 feet per second squared. The velocity then, if we integrate with respect to time, would be negative 5.3 t plus initial velocity, which we now know is 12 feet per second. And this one will be measured in feet per second. Let me keep my units separate here. Then position above the moon, y of t, is going to be negative 5.3 t squared over 2, just integrate with respect to time, plus 12t plus initial height, which again, if she's jumping from the surface of the moon, will be 0. So I'm going to leave that off, and this is going to be measured in feet. Now remember, we're trying to figure out if this woman jumps on the moon, how high above the moon will she rise? So we're going to follow a similar strategy that we did previously. We're going to find the time when this woman's velocity is 0. Remember, at the top of her jump, she's going to stop for one instantaneous moment in time, and that's going to be at the top of her jump. So when her velocity is 0, she'll be at her maximum height. So let's use our velocity equation. We're going to set the velocity equal to 0, and we're going to use this to solve for t. So if we solve for t, we'd end up with 12 over 5.3 equals t. And I'm going to be really careful not to round that at this point, because if I round it and then I round again when I find position, I will have rounded twice and begun picking up error. So I'm going to leave it exact. Let's go ahead and find the height when her time is, I'm just going to leave it like this, 12 divided by 5.3 seconds. So we are evaluating y of 12 divided by 5.3. So using now our position function, we have negative 5.3 over 2 times t, that's 12 over 5.3 squared, plus 12 times t, 12 over 5.3. Now at this point, since I'm only going to round once, I don't mind just plugging that directly into the calculator, and we would find out her height is approximately 13.6 feet above the ground. How much fun would that be? So this woman who has a vertical jump of 2.25 feet on the Earth, the same experiment on the moon, she could jump 13.6 feet high in the air. Very interesting. So again, as we work these problems, you're focusing on these 3 equations, manipulating this system of equations, finding information and coordinating it with the other equations to answer the questions. Again, not so intense solving differential equations, but it does take some strategy and some planning to solve the problems. Now let's consider a horizontal model. So position, velocity, and acceleration still have the same relationship, but I'm going to denote them just a little differently. For our acceleration, instead of using g for gravity, we'll just use a. That'll be constant acceleration. In a horizontal perspective, it's a constant. Then, if I integrate once with respect to time, I'll end up with at plus an arbitrary constant, and you can anticipate that arbitrary constant turns out to be initial velocity. Now, instead of calling the position function y of t, I'm going to call it x of t to represent position to the left or to the right of the origin. So if we integrate here, we're going to end up with, integrate with respect to t, 1/2 at squared plus v naught t plus an arbitrary constant, which turns out to be initial position. Let's use this system of equations to solve example 5. A driver involved in an accident claims he was only going 25 miles per hour. When police tested his car, they found that when its brakes were applied at 25 miles per hour, the car skidded only 45 feet before coming to a stop. But the driver's skid marks at the accident scene measured 210 feet. So if the police applied the brakes when they were testing his car at 25 miles per hour and found that it skidded 45 feet, but at the scene of the accident when this driver claims he was going 25 miles per hour, the skid marks are 210 feet, I think he might be in a little bit of trouble. Assuming the same constant deceleration, Determine the speed he was actually traveling just prior to the accident. Now, before we move on, I want to point out something important. If you're not watching, this will slip by you easily. The distance here is measured in feet, but in the speed, it's measured in miles. And the same thing happens here. So we have a mismatch in our units. We need to use one or the other. Ultimately, we want to determine his speed in miles per hour, so it will be convenient to convert everything to miles. So I'm going to start there, and I'm just going to use this space up here. Let's convert distances to miles, and we'll use those values throughout our problem. So if we have 45 feet and we want to convert that to miles, we know that in 1 mile there's 5,280 feet. So I'm putting what I want to cancel there in the denominator. And in the numerator we have our goal, which is miles. Now, in order not to round and start accruing error, I just type that into my calculator and reduce the fraction. I'd end up with 3 over 352 miles. Okay, so for 45 feet, we're going to use 3 over 352 miles. Let's do the same thing with the 210 feet. We're going to multiply it by 1 mile divided by 5,280 feet. I'm going to avoid rounding as well. This turns out to be 7 over 176 miles. Keeping our numbers in exact form prevents us, again, from accruing rounding error. Now for this problem, similar to what we did with the Earth and Moon problem, we are going to need 2 models. That is the experimental model in the lab and then the actual model at the scene of the accident. So here is the strategy. How are we going to work through this problem? Strategy. Let's begin to determine the constant deceleration of the car from experimental values. Then we're going to use this value to find the velocity of the car from the measured skid marks. At the scene of the accident. Okay, so the first thing we need to do is find the constant deceleration of the car from the lab test. So let's start with our lab model. The deceleration of the car is some constant, I'm just going to call it A. Then our velocity function is the integral of A with respect to t. That would give us AT plus initial velocity. Remember, whenever the brakes are applied, the car is going 25 miles per hour. Then position, we're going to use x of t this time. Integrating with respect to t, we have 1/2 AT squared plus 25t plus initial position. We're going to assume again that that's 0. We'll assume that the moment the brakes are applied, that's the origin on our horizontal axis. Like we did with the moon problem, let's find the time when the velocity is 0. Okay, so remember, the cops are testing out his car. They apply the brakes at t equals 0. The car skids, it decelerates and comes to a complete stop. When it comes to a complete stop, the velocity is 0. So I'm going to use my velocity function. I'm going to set it equal to 0, and I'm going to find t in terms of a. If we solve for t, we end up with negative 25 over a. A is the constant deceleration of the car. Now, we do want to be careful here. Since our initial speed was in miles per hour, this is negative 25 over a hours. So observe, at this particular time, t equals negative 25 over a hours. X, the distance, is 45 feet. or let's be careful, 3 over 352 miles. So we are using our position function. We're setting it equal to 3 over 352, and we're plugging in negative 25 over a for t. Negative 25 over a squared plus 25 times negative 25 over a. So we're putting negative 25 over a in for t in our position function. So this gives us an equation in one variable, and we should be able to solve for that variable. So let's work on simplifying a little bit. We have 3 over 352. Now, negative 25 squared becomes positive 625. Notice we have an a squared in the bottom, but we have an a in the numerator, so those will cancel to leave just an a in the bottom, and we still have a factor of 2 there as well. For the second term, we can write that as negative 625 over a. Let's get a common denominator and combine these two fractions. 625 over 2a minus 2 times 625 over 2a would give us negative 625 over 2a. Let's go ahead and cross multiply and solve for a. We would obtain a equals negative 110,000 over 3, and keep in mind this is in miles per hour squared. So keep in mind I am not rounding in order to postpone the final rounding to the last step so I do not accrue rounding error. So we have successfully found the exact deceleration of the car from experimental values. Now we want to create a model, or we want to update our system of equations to fit the scene of the crime. Similarly, v of t, integrating with respect to t, will be negative 110,000 over 3 times t plus initial velocity. That is what we are interested in finding in order to determine if he was telling the truth at the accident. Integrating once more with respect to t, we have our constant, negative 110,000 over 3 times 1/2 t squared plus v naught t, and we're assuming initial position again is 0. So velocity is measured in miles per hour and position in miles. Now we need to figure out how long does it take for the velocity to become 0. When the velocity is 0, the car will have come to a complete stop. So find the time when the velocity is 0. So I'm using my velocity equations. I'm going to set them equal to 0 and solve for t. We will get t in terms of v naught. Doing the algebra, we'll find 3 v naught over 110,000. Okay, next we're going to use this information to find the initial velocity. This is what we're interested in. When the skid marks are 210 feet long, or as we updated, 7 over 176 miles. So we're using our position function. We are setting it equal to 7 over 176 miles, and we're plugging in this obtained value for t. So looking at our position equation, we have negative 110,000 over 3 times 1/2 t squared. We're plugging 3 v naught over 110,000 in for t, squaring it, plus v naught times t. T is 3 v naught over 110,000. Okay, obviously the calculus part of this type of a problem is easy. The algebra is quite challenging. So let's see what we can do here with the first term. First of all, notice that we have a 3 squared in the numerator, and that will cancel with one of the 3's in the denominator. That's going to leave a 3 in the numerator. Okay, also we have a negative 110,000 in the numerator here, we have 110,000 squared in the denominator here. So it's going to leave behind a negative, and when we cancel, we'll have 110,000 in the denominator. Also, we have a v0 squared that we need to keep up with, and don't forget about that extra 2 there in the denominator from the 1/2. The next term, a little easier, we get 3v0 squared over 110,000. Okay, the common denominator there is 2 times 110,000. So if we multiply the top and the bottom of that second fraction by 2, we'd end up with 6v0 squared in the numerator for 3v0 squared over 110,000. 2 times 110,000, let's call it 220,000 in the denominator. So I'm just getting a common denominator and adding fractions. So isolating v0 squared, you can do that with your calculator. We obtain 8750 divided by 3. We'll take the square root of both sides, and we're only going to recognize the positive square root. And at this point, we can round it. We would end up with 54. And remember, that is miles per hour. So the initial velocity of this person driving the car at the scene of the accident was not 25 miles per hour, it was 54 miles per hour. Using our calculus, we could say that we have busted this guy and proved him wrong. Now that was a pretty involved problem. It was not too intense as far as the calculus goes, but the algebra was pretty challenging, and do keep in mind, we're not deriving those equations each time necessarily using calculus. They are uniform anytime you have a acceleration, velocity, and distance problem. The challenge is in coordinating the information, extracting information from one equation and using that into the other. And this will definitely take some practice. So at this point, your first method for solving differential equations is direct integration. And also you can practice solving these application problems. All right, I hope you learned something new. Good luck on your homework.